I'm kind of offended because I think I'm the only one who did not get an introduction. So I know. Thank you. Thank you. Oh, thank you, thank you, thank you. Um, thank you everyone. Yes, my name is Nadia. I want to start by thanking the TMA for inviting me. This is my fourth RNDS. It's always exciting to be here, connect with old friends, meet new friends, and one feedback I got last year was to make my talks less nerdy. So I'm gonna try my best. I can't make it zero nerdy, but I'll try to maybe like on a scale of 0 to 10, make it a 5. So we'll see. We'll see. Okay. Just a little background. I am, by education, by training, an engineer. I went to school, I did electrical engineering initially, then moved to bioengineering and biomedical engineering for my master's and PhD. My specialty has always been spinal cord imaging. I worked in traumatic injuries initially, then I moved to study in myelitis. And in previous RNDS, I've talked about imaging techniques, advanced imaging techniques in the spinal cord. Some of you may remember diffusion imaging. Last year, we talked about something called magnetization transfer imaging. And so today, I'm going to continue that talk and share with you some recent results and also discuss some challenges we face in spinal cord imaging. And if we have time, maybe introduce a new technique. That's pretty much it. Yeah, that's pretty much it. Okay, so we'll start with some basic anatomy, which I'm sure you all know. The spinal cord is this pathway, right, that sends information to the brain, receives the information from the brain. It's the way I like to think about it as an engineer. It's really like spaghetti, right? It's this bundle of tracts, right? And if we zoom in into these tracts, we find cells called neurons, right? And a fun fact about the spinal cord, it's made of about 13.5 million neurons. And zooming into each neuron, right? A neuron is made of a cell body, an axon, and this structure called myelin, which wraps itself around the axon at multiple locations. And this is how I like to see myelin. Myelin is made of water and lipids, and these are nothing but large molecules. And these molecules do talk to each other, they interact with each other, they exchange energy and information, and we can measure that exchange of energy with MRI, hence the term magnetization transfer imaging. And I'll talk about that in a bit. And we all know spinal cord function, right? The spinal cord is important in so many functions. One of it is our reflexes, touch, motor function, pain, and also temperature sensing. And what happens in the case of myelitis is that some of this function is either slowed down or completely stopped. So here I have two neurons, one with myelin, one with no myelin, and you can see conduction slowing down or completely stopped because of loss of myelin. And we end up with something like this, right? So back to our spaghetti model. We know this by now, right? MRI is the modality of choice when diagnosing myelitis. It's usually done pre and post contrast, and we're looking for this signal hyperintensities. But MRI does have some limitations. It's usually not possible with just conventional MRI to study damage to the axons or damage to myelin. It's also difficult to get the exact extent of the lesion using conventional MRI. And some studies have shown it to have poor correlation with the clinical symptoms. So some of my work has been looking at the relationship between advanced MRI technique and spinal cord function. And for what I'm presenting today, specifically, we're looking for the relationship between magnetization transfer imaging and pain sensation. So as I said, MTI it's an MRI technique. It's basically additional time inside the scanner. And it's based on this notion that these molecules in the myelin, the lipids and the water, exchange energy. And it's believed that the lower energy transfer, the lower the myelin content. Make sense? And so this technique has been around for a long time. It's used a lot in the brain. It's also used in the spinal cord of patients with multiple sclerosis. It's able to detect abnormalities which normally are not detected with conventional MRI. It also correlates very well with disability scores. So in the MS population, it's been used to correlate with EDSS scores and things like that. And I just want to say that all these imaging techniques I usually talk about are not meant to replace conventional MRI. They're just there to supplement it. So whatever MRI does not detect, perhaps these techniques can do it. Okay, so what we did for our study was to recruit we had 23 patients with myelitis and 20 control subjects. This is a pediatric study. It was done at Boston Children's Hospital. And we scanned, so on this graph in the bottom, we have spinal cord levels from C1 to T12. So we scanned everyone using MTI. This data is for the healthy control subjects. And here we're going to compare it to our patient population. And we did see a reduction in MTI, which, as I mentioned, it can indicate loss of myelin content. And the differences were very statistically significant. The next question was to assess pain so that we are able to do correlation between imaging and pain measures. So we use what's called quantitative sensory testing, and it's done with this machine where we place the thermode. For this specific study, we placed it on the dermatome that corresponds to injury level. So if your injury is at C7, the thermode would be placed at your middle finger, for example. If it's C3, it would be on your neck, etc. And this thermode has it changes temperature, so we're able to control the temperature from cold to hot. And and the goal was to get these 4 different measures. First of all, how much cold you're able to detect. So when you first feel cold, when you first feel heat, and also when the cold becomes painful, and when the heat becomes painful. And then so these are the results for our healthy control subjects, and compared to our patients, we did see a reduction in cold detection and cold pain for both for the patients, and higher heat detection, higher pain in the patient population. This means that the patients are more sensitive to cold, but less sensitive to heat. The correlation with MTI was a little embarrassing. So it was not the only measure that showed any significant difference was heat detection threshold, and the correlation was a little bit poor. But some of it could be due to one, sample size being too small, injury level being very different, because here we group in everybody, and also age differences. So we had patients between 7 and 18-year-olds. We also have variability in time since disease onset. But as we collect more data, do more scans, perhaps we'll find different results. We're also looking at vibration and pressure, pinprick, and all kinds of pain sensory testing. So yeah, that's not as nerdy, I hope, as, right? So it wasn't bad. Okay, so now, why is spinal cord so challenging? We heard about Dr. Sweeney yesterday, who literally called it bad. He said spinal cord imaging is bad. And so, I mean, I don't think it's bad. It's challenging, but it's not bad. And one of the reasons is that the spinal cord is really tiny. It's compared to the brain. It's very difficult to image. And the smaller the structure, the lower the resolution. It's like you're trying to zoom in into a very tiny object as you take a picture, so the more you zoom in, the less resolution you have. So that's how MRI works as well. The spinal cord is also deeply located in the body, which makes it susceptible to motion artifacts. So Dr. Greenberg talked this morning about cardiac motion when they're doing surgery. So same thing for MRI, right? We can't stop the heart just to do an MRI scan. We also have swallowing, respiration, and I work with kids, and trying to have a kid, a 7-year-old, stay still in the scanner for a whole hour just to do a research scan is sometimes very difficult. And also, we have another challenge with teenagers who wear braces and retainers. and MRI does not like metal. So if you have retainer or braces, the upper cervical spine will look like this big black hole. No signal. The signal is completely lost when there's metal. Also, our imaging protocols are not standard amongst institutions. We also do use different scanners, so it makes it hard to collaborate, to work on different projects, and also compare data. So it's also an added challenge. It's also time consuming. I mean, MTI, for example, if I were to scan your entire spinal cord, it would be an additional hour in the scanner. But I think it's promising. There's a lot of interest in the community to push spinal cord research. I have a very nice graph here to show you, for example, compared to brain imaging. So in the bottom, we have years from 1960 to about 2018. In red is brain, all the brain papers. So the scale is 0 to 10,000 papers, right? So the brain, for example, you see how many papers are published each year. It's a lot. For spinal cord, which is in orange, it's taken off, but it's about a decade behind brain. And then we have myelitis spinal cord imaging research, and in yellow, it's not 0. It's just because the scale is so large. It looks like it's a 0, but there are some papers out there. Okay, and what's new? So recently, there's been interest in studying the function of the spinal cord with a technique called functional MRI. Functional MRI is used a lot for the brain, but there's been interest recently in doing that for the spinal cord. And it's also same thing, it's additional time in a scanner, but here you're asked to perform a task while they're scanning you. So either tapping your fingers or answering some questions on the screen, and then they measure your blood activity as you're performing these tasks. It's believed that areas in the spinal cord or areas in the brain would activate as you're performing these tasks. And this has gained some popularity. Oh, and it's used, that same machine I showed earlier that we use for quantitative sensory testing, there's this equivalent that's MR compatible that can go inside the scanner and won't get sucked by that big magnet, and it's used to measure functional activity. And it's been mostly popular for pain, and there was a study recently on patients with fibromyalgia, and one of my colleagues just got an R01 grant to do fMRI of the spinal cord in patients with MS. So I think it's gaining more and more popularity, and hopefully we can get something started for myelitis as well. And here, as that same graph earlier, but I took out brain. This is spinal cord imaging versus myelitis versus fMRI. So you see myelitis and fMRI are slowly taking off. I think people are getting more and more interested in doing spinal cord imaging in general, but also looking at demyelinating conditions and also fMRI of the spinal cord. Okay, and I think that's all the science I have for you today. A few thoughts I want to leave you with. So these techniques are promising, but they still in the research phase. They still need very strong evidence. And one question I get a lot is about myelin content. And people say, oh, how much myelin do I have? There's really no such thing as, I can't just put you in a scanner and say, okay, you have 20 pounds of myelin right now, and because of your myelitis, you only have 1 pound left. We're not there yet, but that's the hope. The hope is to develop imaging techniques that can quantify myelin loss, can also look at axonal degeneration, and also correlate that with the clinical status of the patients, and hopefully use all that information for treatment purposes. And the theme this weekend was stronger together, and that also applied for MRI pulse sequences. They do work best in combination. So they all have pros and cons. So what one misses, maybe another one can detect. And that's why I was saying they're meant to supplement MRI. So we learned that spinal cord imaging is technically challenging, but it's very useful structure to study. and it's very important clinically. And to a researcher, a technical challenge and a clinical importance just means more research opportunities. And that's it. So I want to end with more spaghetti, right? So thank you so much. I know it was quick. I know we're running out of time. I'm happy. Do we have time for questions? Save it for later.